Hi folks, welcome back to our third video of this week. So in the last video we looked at moments in two dimensions, and we defined the moment arm as the perpendicular distance from the point of interest to the line of force. And in two dimensions you could have two directions for the moment, clockwise or counterclockwise. Now when you get into three dimensions, you basically have an infinite number of directions. So 3D is much more complicated, but here we go. So let's start off with the generalized expression. Okay. The moment about A equals a position vector, which in 2D is our moment arm, right? So crossed, remember, cross product with the force vector. So this is a position vector that locates the force relative to the point of interest. All right, so what does that mean? So just remembering, cross product is a product of two vectors that produces a vector also, as opposed to the dot product, which gives you a scalar product. Right. So let's look at our previous problem, since we're thoroughly familiar with that. Okay, rigidly attached beam to a wall here. We have some point A about which, oops, that's off the screen, some point A about which we're concerned about its rotation. And we have a force F. Now, we're going to rewrite these in terms of our generalized equation that we put here. Right, so F is going to equal minus F j hat, because it's in the negative y direction according to our typical coordinate system. Similarly, the position vector, now D becomes the position vector R. So this is now RA. Okay, RA starts at A and goes to the line of force. All right, so RA starts at A and continues to the line of force. I should say the line of action of the force. Okay. Now, so RA, to use the nomenclature from our two-dimensional example, its magnitude is going to be D, just like last time, and its direction is going to be positive I, because to the right is our typical positive x-axis. Right? So it has a magnitude, and it has a direction. Okay? Just like the force has a magnitude and a direction. So, using our equation up here, the moment about A is RA cross F, which equals, in our case here, D I hat crossed with minus F J hat. All right, so cross product. Okay, probably been a while since you did one of these, so let's do this in some detail. I'm going to leave this at the bottom as a reference, and I'm going to get rid of this stuff up here. All right. So, the cross product for these three-dimensional vectors is going to be a 3 by 3 matrix. So, so the general form is the moment, the vector, is going to equal the position vector crossed with the force vector. So, this ends up being a 3 by 3 matrix. Across the top of this matrix, you have your 3 unit vectors, I, J, and K. The next row is the magnitudes of the 3 components of the position vector. So that would be Rx, Ry, Rz. The third line are the magnitudes of each of the 3 components of the force, Fx, Fy, Fz. All right, that's the setup. That's always the setup. Your directions, your unit vectors on top, I, J, K in order. The second row, the magnitudes of the 3 components of the position vector, and on the third line, the magnitude of the 3 components of the force vector. All right, so now to evaluate this, people have different ways of doing it. I'm going to give you one. If you have another one that works, that's just fine. As long as it's legitimate, we're good. Okay, so I'm going to write it down first and show you where I got it. I times the quantity Ry Fz minus Rz Fy. All right, so the way this goes is to evaluate I. It's kind of a shortcut method. You get rid of these, and then it's the upper left corner times the lower right corner minus the upper right corner minus the lower left corner. So if I was to write this on the side, okay, I, J, K, Rx, Ry, Rz, Fx, Fy, Fz. What we're doing is crossing these out and multiplying this way and multiplying this way. Okay, so this is the first term. And then there's plus j. And these are done the same way. Sorry, that's going to be minus j times rx fz minus rz fx, and then plus k hat times rx fy minus ry fx. All right, and you can go about doing these the same way. Like for j, the j column goes away, and it's upper left times lower right minus upper right times lower left. Now, you can also do this by going across the rows. I times ry times fz, j times rz times fx, and k times rx fy, and then minus going in the other directions. Right? That's the way I used to do it. Students seem to find this method easier and seem to have been aware of it from other classes, so I just went with it. All right, so whatever works for you. A check here is that in the I row, there should be no x components. In the j row, there should be no y components. And in the z row, there should be no k components. All right, so using this on the problem we just did, okay, we had the moment about A equal to unit vector, or the position vector RA crossed with the force. Now remember, this was d I hat, and this was minus f j hat. All right, so if we put it into this matrix form, always I, j, and k at the top, then the components of the position vector, d, and there's no 0 or k component, and then the components of the force vector, there's no x component, there's minus f for the y component, and 0 for the j. Okay, so if we go through this, up here, okay, I times ry, which is 0, minus rz fy, which is 0, so I is 0, plus j hat. J hat is rx, which is d, but times fz, which is 0. And then minus rz, which is 0. Right? So this is 0. Plus k hat. K hat is rx, which is d, times fy, which is minus df, minus ry, fx, which is 0. So this is going to equal minus d f k hat. All right. So that means our direction is the minus k direction. So what would that mean in terms of rotation? Let's take a look at that. Okay, so recalling our initial problem and the force applied here, minus k means it's going to tend to rotate in the clockwise direction, right? Because we said negative is defined as clockwise, so it's going to want to rotate this like this, which makes sense, right? That's what we would expect. So the direction of the rotation is the direction of the axis about which the rotation occurs. So for our case, it's the z-axis coming out and going into the page. So to get direction, probably remember from physics, RHR, right hand rule. Okay, so you put your fingers in the direction of the first component, which is the position vector, and then curl them in the direction that the force is acting. So you put them in the direction that the position vector is going, then curl in the direction of the force vector, and your thumb points. So if I'm doing it into the board here, it goes in and turns, and it tells me that the thumb points into the board. So right hand rule in 2 dimensions anyway is pretty straightforward. Gets a little trickier in 3 dimensions. All right, now so now let's generalize this a little bit more. We're taking some point O, some force F, okay, we want to find the moment of F about O, and we draw a perpendicular. All right, and we call this R0 because it's the position vector from the point O to the line of action of the force. And this is could work perfectly legitimate, but you may not know the coordinates of this. You may not know the direction. So what you can do is, instead of drawing that, take that same force line and from O, take a point O and draw a horizontal R0. All right, so when you draw a horizontal R0 to the line of action of the force, you know R0. You know it's going to be I hat, something, it's going to be in that I hat direction. it doesn't have to be horizontal. You could, from point O, here's your line of action of the force again. You could pick 45 degrees. You could pick a line on R0 at 45 degrees to the horizontal. Again, the purpose of that would just be for you to know the direction of this, to give you at least to eliminate one unknown. Here, you don't know direction, right? And the beauty of the cross product is what it's going to do. What it does is it takes that geometry into account. So no matter which situation you choose, if you have the correct coordinates in there, you're going to get the same answer. So it's an important point, any vector from O, the origin or point of interest, to the line of action of F will yield the same result. All right, so that's the 3D most generalized version. Thanks very much, and we'll see you again soon. Bye-bye.